All right, so this is lesson 4.3. We're going to be doing part 2. I'm just going to quickly recap part 1. If you want to go and watch the part 1 video on the first derivative, just watch my previous video. So in the first video, we looked at how the first derivative tells you about whether a graph is increasing or decreasing and how you can use that to figure out whether a critical number is a maximum or a minimum. We're going to continue with our exploration of derivatives and how they help us understand what graphs look like. But this time we're going to be looking at the derivative of the derivative, so the second derivative. So let's scroll down past what we did last time and head to this picture here. So when the graph is shaped like a smiley face, I always like to use a smiley face analogy because it helps you remember the signs, okay? The derivative is actually getting larger, or it's increasing in value as we read the graph from left to right, right? It starts out as a negative number at first, and then it goes to 0, and then it turns positive, right? So the derivative is actually increasing in this picture. It's getting larger, right? We start off with a negative slope, then we hit 0, and then we end up with a positive slope, right? So the value would be getting larger and larger and larger as we go along the graph, right? The second derivative is telling us the rate at which f prime is changing, and so because it's increasing, this is going to be positive. Okay, so whenever you have a smiley shaped graph, your second derivative is going to be positive. So I'm going to use yellow today to describe any kind of positive second derivative. Okay, we call this concave up. Okay, so this shape, this smiley face shape, is called concave up. In contrast, if you had a sad face shape, your derivative is actually decreasing, right? If we look at the derivative here, it starts out being positive, it then hits 0, and then it turns to negative, right? So the value of the derivative is going down. So that means the second derivative would be negative because the value is decreasing. So let's fill in those. Okay, so whenever you have a sad face shape, okay, our second derivative is going to be negative. And it's kind of easy to remember that because being sad is kind of like being negative, right? And your smile is facing downwards, or your mouth is facing downwards, so you call it concave down. So all of those kind of go together. I think it's kind of easy to memorize, all right? So concave up looks like a smiley face. Your second derivative is positive. Concave down, your second derivative is negative. Okay, it looks like a sad face. And then we give a special name to places in a graph where it changes concavity. So let's say in this graph here, we start with like a kind of a frowny face shape, but then it changes to a smiley face shape at this value here. So at this point, there's a switch in concavity, and we call that an inflection point where we change signs, okay? So an inflection point, you have to know that word, and you have to be able to, and we'll do some examples of this, but it's where the concavity changes from positive to negative or from negative to positive, okay? So in this section here, we are concave down. That means the second derivative would be less than 0 in that section. And here we are concave up. I'm going to use CU for short, concave up. And then the second derivative would be positive in this region. So at this inflection point is when, so the inflection point is right there. That's where f double prime changes signs. Okay. All right. So we can actually use the second derivative to confirm the first derivative test, or you can use it to figure out where a critical number, like whether a critical number is a maximum or minimum or not. Okay, so if a critical number happens to be a place where the derivative is equal to 0, then have a look at this concave up picture that I have here. Okay, if my critical number is here, right, this is a local min, because you're going to be at the bottom of your smiley face. Okay, so if the second derivative is positive and we're concave up, the critical number is a local minimum at x equals c. Okay. And if you have a sad face shape and you have a place where the derivative is 0, that means it's going to be a local maximum, right? Because you're going to be at the top of that sad face shape. I would recommend not memorizing this and more trying to work towards understanding this so that you can just recreate these kind of pictures on your assessments. And then finally, if you have a place where the second derivative is 0 or undefined, you have to do some more testing. So you will have to then use like the first derivative test, for example. So it doesn't really mean anything. It's kind of like inconclusive. Maybe you have a higher multiplicity there or something like that. Needs further testing. So the second derivative test here can only get you so far. Sometimes it helps you out and tells you whether you have a local min or max, and sometimes you just need to do some more testing. But it's good to kind of understand the shape a little bit. Needs further testing. Okay. All right, so let's do an example here, just with a picture, okay? Students often find these difficult. So this time I'm giving you a picture of the derivative function, okay? But we're going to answer some questions about the original function, okay? And even though we can't see it. So we can only see the derivative function here. We cannot see the original function, okay? So question A, it says, on what intervals is the graph of f of x concave up? So first of all, what I like to do, or tell students to do, is just write down what that means. So if the graph is concave up, that means that the second derivative is positive, right? If the graph is concave up. It also means that the first derivative is increasing. Because remember what the second derivative is, it's a rate of change of the derivative. Okay, so we're looking for places on this graph where it is increasing. So I see that happening right in this section here between 2 and 4, right? The graph is increasing there. It has a positive slope. And so, right, the second derivative is the slope of the slope. So we're looking for where the slope of this graph is positive, essentially. Okay, so the answer would be for x between 2 and 4. I don't know what that beeping is. 1 second. Okay, let's hope that's nothing. All right. All right, so I'm going to just keep erasing my highlighting after each step. All right, so that's the first one. Second one, on what intervals is the graph of f of x? Even though we can't see it, where is it concave down? So again, we want to just write down what that means. So if we're concave down, that means our second derivative would be negative. And it would mean the first derivative, it would be decreasing, or would have a negative slope. This tangent line would have a negative slope. So we're looking for places on this graph that we can see where it's decreasing or has a negative slope for the tangent line. Okay, so I'm going to highlight those regions right now. Right, we'd have a negative slope for this region here and also for this region here. So anything less than 2 or greater than 4, right? So we would put for our answer, x is less than 2 or x is greater than 4. All right. It says, state the coordinates of any inflection points. So inflection points, remember, are when the second derivative changes signs. So that means it's where the slope, if I'm looking at this graph, it's where my slope would change, right? From positive to negative or negative to positive. That's happening at 2 points here, right? At x equals 2 and x equals 4, right? From x at x equals 2, it changes from a decreasing graph to an increasing graph. So the slope would change from negative to positive, right? And then same at 4. All right. And then it says, state the x-coordinates of any critical numbers on the interval 0 through 6. So remember, critical numbers are endpoints, which we don't have here. Places where the derivative is undefined. We don't have any places here where there's any undefined points. So it's only going to be for this graph any places where our derivative equals 0. And we can just look at the graph to find where it's 0. There's 2 spots. one at 2 and one at 5, right? Where it's hitting the the x-axis where it has a value of 0. Okay. All right. Let's move on to E. I think this is the hardest part. I recommend making like a little table here to understand this better. Okay, so it says state the x-coordinates of any local minimums or maximums of the original function. So the hard part here is because we can't see the original graph. So what I always tell students is to just make yourself like a little number line and do some tests. I feel like the visual is really helpful. So we have two critical numbers, right? Places where our derivative is equal to 0. One happening here at 2 and the other at 5. I'm wondering whether we have a minimum or maximum at those two values, okay? Those are the only two places we can have a min or max because those are the only two critical numbers, right? We don't have any places where our derivative is undefined. We don't have any endpoints, right? So those are the only two values. So we're going to test our first derivative, and we're just going to test by looking at the graph. We know it's 0 at these 2 points, but we're wondering about what's happening on either side, right? So before we get to x equals 2, when x is less than 2, right, the derivative has positive y values, okay, positive values. So we're going to have a positive result here. Then we're going to have a positive result here, right? These are still positive numbers, positive values. And then finally over here, there's negative values for the function on the other side here. So what does that mean? I'm going to just color code these. What does that mean for original function that we can't see? I always find it's helpful to draw some arrows. So that means the original function that we can't see must be increasing in this region, still increasing in this region, but then decreasing in this region. So that means just by the shape of the graph, it's going to look something like going up, plateaus for a second, goes up, and then goes down, right? And we've got a local maximum at x equals 5. So notice I didn't memorize anything there. I'm just like using the positive and negative values to kind of sketch a little shape for myself and understand that the maximum is happening right here at 5. Right? Okay. All right, so we have 2 more examples to go through. One of them continues from example 1 from before. So if you haven't done the first part of example 1 yet, I would go back and do that because I'm going to be using some of the results here. It says find the intervals where the function is concave up and concave down. What are the points of inflection? So we've already done the first derivative test. We've already found where the local minimum is here. We're now going to do the second derivative. So just as a recall, the first derivative was x to the power of 3 minus 3x squared. The second derivative is going to come straight from that. It's going to be 3x squared minus 6x. Okay, I always recommend factoring so you can find the zeros. So we can pull out a 3 and an x. Okay, so what this tells you is not the critical numbers, but the places where the concavity could change, right? Remember the second derivative tells you about the concavity. So we can, places where it's equal to 0 could be places where it changes from positive to negative or negative to positive. Okay, so we can call these possible, because it's not for sure, inflection points. I'm going to do IP for short at x equals 0 and x equals 2. Okay, those are the 2 zeros there. All right, so we're going to do some tests to find out. All right, so I'm going to make a number line here. I'm going to test before I get to 0, between 0 and 2, and then after 2. Okay, so I'm doing the second derivative test this time. I know it's 0 at these 2 points. Okay, it can only change signs at those 2 values, right? Because that's where it's equal to 0. So let's test, right? And you would pick any like nice number that's less than 0 to start with. So let's test, I don't know, x equals -1. We're going to plug it into the second derivative. When I plug -1 into here, I get a negative times negative, which is a positive number. Okay, so that means we've got a concave up shape. Okay, it's looking like a smiley face. The original graph is looking like a smiley face in that region, okay? When I test something in between 0 and 2, I don't know, like 1 seems reasonable to me. Plug that in, I get a negative value for the second derivative. So that means my original graph is looking something like a sad face, concave down shape, okay? And then finally, choosing something like, I don't know, 3. Okay, plugging that into the second derivative there, I'm going to get a positive value. So that means I'm getting a concave up shape. Okay, so I'm concave up for x less than 0 and x greater than 2. Concave down for 0 less than x less than 2, right? In between those two regions in the blue zone there, okay? And I have inflection points where it changes concavity. So we have inflection points at x equals 0 and x equals 2. Okay, it happens to change signs at both of those, so we have inflection points at both. All right, let's do a slightly harder one in terms of the algebra here. We're going to do one with an exponent that's a fraction, okay? But same idea. I just want to show you some of the algebra behind how you would determine this compared to a polynomial where you need to factor, okay? All right, so here is a function. It has a rational power, and we are going to find the inflection point. So that means we have to find the second derivative. So I'm going to obviously go ahead and find the first derivative because that's a good place to start, right? This is a product, so we need the product rule. 2/3 is going to come down. We have x to the negative third, and then leave this alone. Okay, and then plus x to the 2/3. Okay, now one little strategy here that I find really useful is creating like a one term for your derivative so that you can find your second derivative a lot easier. So the way that you would do this, firstly, is just make it into a fraction to start with. So there's a negative power there, so I would pull that into the denominator and then create a common denominator. So we've got 2 and then x minus 5 all over 3 to the power of x. Sorry, 3 times x to the 1/3 plus x to the 2/3. Now I'm going to create a common denominator here to make this all one term. When you do this, it's much easier to do the next derivative, but it's also a lot easier to find the zeros, okay, because everything's in one term. So you can look like at the denominator or the numerator in isolation a lot easier that way, okay? And actually you'll see some nice things come out here. So what we get is 2 and then x minus 5 plus, and when you multiply those powers together, you add the exponents and you actually get 3x, which is kind of nice. And then the entire denominator would just be 3x to the 1/3. Okay, so you can pull those together now because they have the same denominator. Now we can collect like terms. So we get 5x minus 5 all over 3 times x to the 3rd. Okay, so if I was interested in critical numbers at this point, I would determine x equals 1 and x equals 0 would both be critical numbers. Because, yeah, it would look at where the denominator and numerator are equal to 0, but we're not doing that. We're just going straight ahead into the second derivative because we're looking for inflection points here. So now I'm going to go ahead and do the second derivative. Okay, and because this is a quotient, I need the quotient rule. So the structure of my answer will look like this. And the derivative of the numerator is 5. And then it's minus, and then same thing again that's going to happen. The 1/3 is going to come down. It's actually going to cancel with the 3, which is kind of nice. But I'll have x to negative 2/3 times 5x minus 5. Just realizing here I made a mistake with my... This should be a 10. I forgot to if you're following along here, I forgot to multiply the 2 with the 5. And so this should be a 10 here. So I'm just going to make that correction right here. So I misquoted you the critical numbers. They should be 2 and 0. Should be a 10. Okay, that don't have to make too many changes. That's good. Okay, all else is looking good. And then I'm going to square the denominator, which will give us 3 squared is 9. And then x to the 1/3 squared is x to the 2/3. Okay, now that looks pretty messy and kind of nasty, but we can actually clean this up a lot by multiplying by a strategic number in the numerator and denominator, essentially by multiplying by 1, okay? I'm going to get rid of the negative powers this way too. So I'm going to choose x to the 2/3. Now I'm allowed to do this because I'm just multiplying by 1 essentially, but what this is going to do is it's going to cancel that out and it's going to make that into an x. Okay, so you can do this to cancel out any negative powers if you ever end up with them in your denominator or numerator. It's a useful little trick you can do. Okay, so I'm going to end up with here 15x for that first term. And then the negative 2/3 plus positive 2/3 is just 0. So it'll be x to the 0, which is 1, minus, and then 5x minus 10, all over. And then I'll have 9, and then I add those powers to make 4/3. Okay, so look how clean that looks. It looks pretty nice. I'm going to collect like terms here, and then I've got some nice values to work with. Plus 10, all over 9x to the 4/3. Okay, so there are 2 places where I need to look for my not critical numbers, but for my inflection points. So we have possible IPs, inflection points, at x equals -1. That's where the numerator would equal 0. And so then the entire second derivative would be 0 if the numerator is 0. Also, if the denominator is 0, it's undefined, and that's also a place where you could have a change in concavity. So we want to check both of those values, and that's where we want to do our test. Okay, so we're going to do a number line here. We're going to test values at less than -1, between -1 and 0, and then everything greater than 0. Okay, be strategic when you're testing, because we have a fraction here for our second derivative. So when we're testing our values, let's look at the numerator and the denominator. The denominator is always positive, no matter what x we plug in, because it has a even power in the denominator. Okay, so that's kind of nice to know, because I basically don't even have to test it. I just have to test the numerator. So I'm going to choose x equals -2 for my first test. Let's see, we're here, undefined here. Okay, so if I plug in -2 into that numerator, I'll get 10 times -2, which is -20, plus 10, that's a negative value. Okay, so my original function would be a sad face or concave down in that region. Okay, here I'm going to test x equals -1/2. Okay, plug that in. I'm going to get -5 plus 10. I'm going to get a positive number. Okay, that means I'm going to have a concave up sort of a shape in that region of the original graph. And then testing something, I don't know, like 1. Okay, plugging that into the numerator, it's going to give me a positive number. So I don't have a change in concavity at 0. Okay, so I'm going to have still a happy face sort of a shape for my graph. Okay, so there's only one inflection point, and that happens to be at x equals -1. So that's the answer to the question. Just for practice, you could go ahead and try doing the first derivative test too. You can look at my answer key for the results of that. I added them in there. Okay, but yeah, that's the end of this lesson.